Okay, so I want to go over some of the stuff we did yesterday, not yesterday, whatever, last time, and then uh, keep just working through carboxylic acid derivatives. All right, so what am I going to get for the first thing? What? We're going to get an ester. All right, so we're going to lose the OH, and we're going to add the oxygen from the alcohol and everything attached to it to make an ester. So then what am I going to get for this next one? What functional group am I going to get?
A student in class. A ketone.
You do. Right? It's PR. Yeah, not BR. It's PR. My handwriting's bad, but that one's clearly a PR. Clearly. That's not on me. And then what about this last one? Now with the correct reagent. You get an aldehyde. Okie doke. So D feels like free money, right? So what's D? How do you go from an acid chloride to a tertiary amide? Secondary amine. I like this new energetic Zoom I have. Like, I don't know what happened. They're like the last three lectures. Time for me to come out of my shell. Right, this is my time to shine. Closers is what they are. They're going to close the year strong. All right. So we know we need a secondary amine to turn an acid chloride into a tertiary amide. So if we have that, um, what, I guess, where do acid chlorides come from? Yep, it comes from thionyl chloride, SOCl2. What does that have to react with? A carboxylic acid, right? So again, so this is one of those times where if you're just like, oh, I know that acid, I only know one way to make acid chlorides, that kind of fills in like two blanks before the acid chloride because you're like, well, I know I have to have thionyl chloride, and I know that thionyl chloride has to react with um, a carboxylic acid. All right, you've already passed this exam. How do you turn a primary alcohol into a carboxylic acid? So there's a lot of ways. We could do sodium dichromate and sulfuric acid. You could use chromium oxide and water. You could use KMnO4. There's a lot of different ways. Or by a lot, I mean 3. Whatever. All right. So far, so good. Next up is anhydrides. So anhydrides, this is the second most reactive carboxylic acid derivative. And it's an oxygen that shares 2 basically carbonyl groups. Is it anhydride? Because the way that you make an anhydride, right, kind of the simplest way, is you have 2 acids and you remove water. That's the an, right? No hydride, water. You take water out, and that makes your anhydride. So anhydrides kind of get classified like ethers, right? Remember ethers, you had symmetrical and asymmetric ethers, right? Where anhydrides are similar. So for anhydrides, right? Oops. Right, so they can be symmetric where the group there's a plane of symmetry down your oxygen, right? So the molecule just folds on itself perfectly. Or now you'd be like asymmetric, so close. Or this can be mixed. They can be mixed. Because the term mixed is coming from the fact that you've mixed 2 different carboxylic acids together to make this anhydride. Again, I don't make the rules. I live comfortably beneath them and tell you about them. Right? Like I'd be like, yo guys, can we just make this all like, consistent? They didn't come ask me. It's been easier. But no. Right? So mixed anhydrides, the 2 groups aren't the same. So I'm going to show you one way to make anhydrides, and we're actually going to make them from acid chlorides. And this is a way to make mixed anhydrides. So you can take an acid chloride and then a carboxylate salt. We'll just put an M there, make it actually legible. An M, and that will get you a mixed anhydride. M here is usually, lithium, sodium, or potassium. So we have our metal just chilling. So we can use our negative charge to attack the carbonyl carbon of the acid chloride. And our metal is also going to be hanging out here, just serving as a counterion. Now, we've got a such intermediate. What do they want to do? They always want to collapse back down. So our O minus, those electrons are going to come down and kick out the chlorine. Now, the acetate that you just added, or the carboxylate you just added, is also a pretty good leaving group. So there's a non-zero chance that you can push the carboxylate back out and remake the acid chloride, but then the reaction just tries again until it makes the anhydride. So this first step here, I could actually say is in equilibrium, right? It goes back and forth, 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 back and forth. And then every so often it spits out the chloride and goes and makes the anhydride, and then the reaction is done. So it can spit out the thing you don't want, but eventually you'll get what you want in the end. Just takes a little bit of time. So anhydrides are less reactive than acid chlorides. So they do a few less reactions, right? Basically, the thing that you use anhydrides for is you use them to make esters and amides, right? So take an alcohol, you have an anhydride, and you're just going to make an ester. Amines, same thing we saw before, right? If you have a primary amine, you're going to make a secondary amide. If you have a secondary amine, you're going to make a tertiary amide. And again, tertiary amines don't work in these reactions. Mechanistically, same thing we saw for the acid chlorides in terms of a mechanism. We'll do the ester example. right? So same kind of thing that we did with the acid chloride, where our lone pair is going to add, push electrons up, but we're going to skip that charge structure. We're going to go kind of right to, try to give myself the right way to draw this. There we go, that'll work. Right, because I don't want to have O minus and then a positively charged and then like an acidic proton. All right, so here's our tetrahedral intermediate. Right, lone pairs on, let's say, this oxygen can kick down, push out the acetate. And then we can use our acetate to pull off that proton and give us, give us our ester. Plus generates a little bit of carboxylic acid. So symmetric anhydrides are easy because, well, they're symmetrical, right? It doesn't matter which carbonyl carbon you add to, you always get the same product, right? Now this changes when you have a mixed anhydride, right? People are writing furiously. Oh, wait a second. I need some jars to break and some rupees to come out. Like I could really like sell this as my life now. And a green hat. Great. All right, we good now? All right. So, right, if you have, right, we have our same dumb little alcohol here. That's very smart. Its mom loves it, but you know. Right, and I have this anhydride. Those two carbonyls are pretty close to one another, right? In terms of like sterics, right? There's not a whole lot that differentiates, let's say, blue dot here from red dot, right? They're pretty similar. So half the time, you're going to add to the blue dot, and the other half the time, you're going to add to the red dot, right? Not great, right? Because what if you only wanted to make the red ester, and you're stuck making the blue ester half the time, right? Not great. So, one, you can just make sure it's symmetric, not have a problem. Or two, if you have to use a mixed anhydride, you can differentiate the two sides sterically. You can make one carbonyl carbon hard to get to, and one carbonyl carbon significantly easier to get to. Right? Tert butyl is kind of our go-to big thing. Right? So if you use a big group like a tert butyl, it's going to block addition to that blue carbonyl carbon. and only allow you to add to the red side. So then you'll only make the red ester. The reason this can be important is, what if your acid, again using like the mythical example of like, what if the acid took you like 2 weeks to make, right? And you're like, well, the acid chloride didn't work. I need to make the anhydride, and I'm not going to make a symmetric anhydride because then I throw away half the acid that I worked so long to make. I can make a mixed anhydride and just make sure I use a big group on the one side to make sure I only add to the one carbonyl carbon that I want, right? So for like simple examples, the like your natural inclination of like, duh, just make the symmetric one is right. But when things get more complicated and your acid becomes more valuable, you don't want to throw half of it away every time you do the reaction. That's basically it for anhydrides. There's not a whole lot going on here. Now on to esters. Esters, not just your great grandmother's name, right? So we all know esters. We all tolerate them, I guess, right? You got a carbonyl carbon bonded to O carbon. Esters are pretty stable, right? You make them, put them in a jar, they'll stay esters for pretty much ever. But they're still able to do a number of different reactions. So there's something that you can make, carry it through steps, but when you need it to react, it can react with the right reagents. Right? First thing we're going to do is we're going to take a trip down memory lane and talk about naming, something we haven't talked about in a while. Right? So the first thing to look at, I'll redraw my ester from above, is esters are broken into two pieces, right? You have the acid part of the ester and the alcohol part, right? So you have the part of the ester that originated from a carboxylic acid and the part of the ester that originated from an alcohol, right? So if you think about a Fischer esterification, if you were going to make this ester, right, you would take this carboxylic acid and you would have it react with this alcohol. To make your ester, right? That's where the acid half in the alcohol half come from, is what are the pieces you would need to make this with a Fischer esterification, right? So when we name an ester, so when you name an ester, you're going to list the alcohol part, then you list the acid part. So great, keep it the same thing. Great, so the name is going to be alcohol, then acid. The alcohol part is really easy. You just treat the carbon group on the oxygen as a substituent. So I've got one carbon, that's going to be a methyl. So this is methyl. And then you treat the acid side like it's a carboxylate salt. So you count the number of carbons, have 3. That's propan and then O8. So it's methylpropanoate. All right, so for the first one, 2 carbons on the alcohol side, that would be what? Ethyl. And then the acid side has 2 carbons as well. So this is ethyl, ethanoate. Right, for the O8, I'm just chopping the E off of the hydrocarbon name and then adding O8. Right, so the next one, 3 carbons is propyl. 1 carbon would be meth and O8. So propyl methanoate. What is it when you have a benzene ring as a substituent? Phenyl. So phenyl, that's phenyl. This, where it's an OH, is phenol. So then this is in 1, 2, 3, 4. This is phenyl butanoate. This is ethyl. What's that called? Benzoic acid. I bring that up because this side over here is benzoate. So this is ethyl benzoate. Naming esters not too hard, right? Cyclic esters go in a big bucket called lactone. So every cyclic ester is an example of a lactone. other than knowing that these are called lactones, I'm not going to have you name each individual one. They get like Greek letters, like the first one's like beta lactone. And then there's like, I think the next one's delta, then gamma, yada, 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 as you go up. But we're not going to bother.
The question was, are there alpha lactones?
I don't think there's an alpha because I think it's too strained, but I'm not 100% sure. Maybe someone has made it and I have not seen it, but it's not very common if it does exist. I will, so just to point out, you can make these, particularly like 5 and 6 rings, be like a Fischer esterification, right? You could take sulfuric acid and heat, right? Your alcohol and your ester are in the same molecule, so it'll just wrap up itself, like wrap around on itself and make an ester. So, right, I can count 1, 2, 3, 4, 5, 6. So I'll make a 6-membered ring from carbonyl carbon to the oxygen will be six atoms in the ring. Right, and then any groups we have along the chain, we would just have to make sure we put on the product in the right place. So let's say we had right, you would just say, all right, how big is my chain? 1, 2, 3, 4, 5. Again, you don't have to draw your oxygen where it's like at the top of the ring. I just am for consistency's sake. But wherever you put the oxygen is perfectly fine. Now we can number around 1, 2, 3, 4, 5. Right? So as I have numbered, carbon 2 on my starting material has 2 methyl groups. Carbon 2 should have 2 methyl groups. Carbon 4 has a methyl, but it also has stereochemistry. So we need to make sure that our stereochemistry matches in our product because we're not doing anything to that carbon-oxygen bond, so that stereocenter should stay the same. So 1, 2, 3, hydrogen makes 4. Is that R or S? No pressure. Just all of Organic One's writing on this. This is S. So we need to make sure that when we put our methyl group in our product that it's also S. So that should just be S, right? Oxygen's 1, chain is 2, methyl's 3, hydrogen makes 4, and that's still S. Fair? So esters do four main reactions. They do transesterifications, they do saponifications, reductions, and then addition reactions. So we're just going to work through this list. We will see how far we get. We're just going to work through here until the end of the day. We will not make it all the way through, sadly. All right, so transesterification changes the alcohol group of an ester and can be done under two types of conditions. You can have acidic conditions, and these are very similar or almost exactly the same as the Fischer esterification. You have your ester group, whatever it is. You have your alcohol. You treat it with sulfuric acid and heat, and you swap your ester groups. So you'll generate alcohol from your alcohol side of your ester and make a new ester. Now, this is going to be an excess to make sure we drive the reaction to completion. We can also do this with like a cyclic ester, a lactone, which we just learned, right? So here, right, we'll have our alcohol, sulfuric acid, and our heat, and we're going to open up our lactone. So we're going to end up making an ester, right? And then if we count out 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, right? This oxygen right here in green is this oxygen here. So with a lactone, you're going to have your alcohol and your newly formed ester attached to each other. So the alcohol that you make from breaking the ester and doing the transesterification is still attached to your ester. And then we can also do transesterifications under basic conditions. So under basic conditions, you're going to have your ester of some sort, and then you're going to have an alkoxide. The metal, again, is the big three, lithium, sodium, or potassium, and you're going to switch your ester for the alkoxide and generate a new alkoxide. And again, this is an excess for the same reason. We have to drive the reaction to completion. And if you have a lactone, everything is pretty much the same. Right, we'll just make them, but here we have to have the then H plus because we need to protonate the alcohol that we generate when we open. So let's count real quick. 1, 2, 3, 4, 5. Yep, okay. So that's right. Right, so again, this oxygen here is this oxygen here. The reason we need the then H plus is if you don't have it, when you open your lactone, you're going to have the alkoxide, and you don't want the alkoxide, you actually want the alcohol. So we have to add H plus so that it will protonate the alkoxide and give you the alcohol. So first step is transesterification. In transesterification, you change the alcohol part of the ester. So you go from, let's say, A methyl ester, you add a different alcohol, say 1-propanol, sulfuric acid, and heat. And you generate an ester, but you've just changed the R group on it. Just kind of rearranging deck chairs on the Titanic, right? Just moving stuff around. If you have a lactone and you do this, you end up with your alcohol. So I should point out, you do generate methanol, right? You generate this alcohol here, is that there. The alcohol fragment ends up being just an alcohol. When you have a lactone, the new ester that you make ends up attached to the alcohol fragment. So here you end up with like OH, 1, 2, 3, 4, right, where this oxygen right here, make it green, is that oxygen right there. Right, so they stay attached to one another. Hopefully you felt very confident in the Fischer esterification mechanism, because this is the exact same thing, right? We're just going to do it again to hopefully forcibly smash it into your minds. So same thing, I have an alcohol and a strong acid. That alcohol is going to get protonated, and that's going to do the heavy lifting of moving protons around in our solution. Just like with the carboxylic acid, the carbonyl oxygen is the most basic, so we're going to protonate that one. Now it's easier to add to the carbonyl carbon because we've protonated the oxygen and made that carbon more positive. So the lone pairs on our oxygen can add, we'll push electrons up. So here, we know that our overall goal is to switch our ester, our alcohol fragments on our ester. So we want to end up protonating or making the oxygen that was in our ester the good leaving group. So the one that had the carbon fragment on it, that's the one that's going to pick up the proton and become a good leaving group. Now we can use our lone pair on our OH to push out that alcohol now, that good leaving group. Right. And then we can take another, in this case, methanol, grab a proton. Right. We regenerate the protonated alcohol that we need to go do the next reaction. And when we have our new ester that we wanted.
The question was, why doesn't the alcohol we just generated pick up the proton off the carbonyl oxygen? Why do we use a methanol?
It totally can. You can use an alcohol that you just made to pick up a proton, but you're going to have, just like with Fischer esterification, you're going to have this alcohol in excess. So there's just way more of it. So, right, you do spit out that ethanol, but there might be like 1,000 methanols for every one ethanol. And it just ends up, so more likely that a methanol will grab it. And two, it is a little cleaner to regenerate that same protonated alcohol that you used up here in the first step. But yes, that ethanol could grab that proton, but more than likely it should be the alcohol that you're using to swap with the ester. So this is the exact same mechanism as a Fischer esterification, except for instead of starting with an OH, right, a carboxylic acid, you're starting with an O ethyl. But where all the arrows go and where all of the protons are and everything, exactly the same mechanism. So I just wasted 4 minutes and taught you nothing. I reinforced something that you should already know to make sure it was really in there. That's what we did. That's a good use of time. All right. Next up, the basic transesterification. All right, so we've already seen some examples. Right, pretty straightforward. You have your ester, you add an alkoxide, and then you make your new ester, plus you generate another alkoxide. So the mechanism here is a pretty straightforward tetrahedral intermediate mechanism. So we're going to have our ester, our alkoxide is a strong enough nucleophile that it can add directly to the carbonyl carbon, push electrons up. Right, I don't have to do anything to the carbonyl carbon to make it more reactive. This is going to give us our tetrahedral intermediate, right, our O minus. We're going to have the metal hanging out by it. And then here. So at this point, right, we know our tetrahedral intermediate wants to collapse. It has two choices. It can push off the oxygen group that was already on the ester, and that's what we want it to do. That gets us to the product, right? But it also can push off the group we just added, and that takes us back to the starting material. So since this reaction is in equilibrium, we need to use an excess of our alkoxide that we want to add to make sure that our tetrahedral intermediate pushes out the right group, right? So when we have an excess of our alkoxide, that's going to make it so it favors pushing out the oxygen group that was already on the ester when we started. So with that, I think we're done for the day. So I will see you guys all next time.